Today we shall discuss the proposal for building an India-based neutrino observatory. In the last few years, a number of institutions, research institutes, universities and IITs have come across with a proposal for building an underground observatory for neutrino and other experiments. So, there are two purposes. It is an underground observatory where a large number of experiments can be done, and also there is a specific proposal of having an experiment on neutrinos, studying the neutrino oscillations with atmospheric neutrinos. So, many of our institutes are involved in this, and today we have Professor M.V.N. Murthy from the Institute of Mathematical Sciences, who was involved with this project right from the beginning. So, Professor Murthy, what is your idea about the India-based neutrino observatory right now?
As you know, we started discussing the idea of India-based neutrino project seriously from 2000, when many neutrino physicists met during a workshop on high energy particle physics and phenomenology. Earlier also there were some sporadic discussions, but a focused discussion started from 2000, and it was felt that given the history and the pioneering work done in neutrino physics in this country, especially the underground laboratory that were the results which came from Kolar gold fields, it was felt that one should have the tradition continuing. Not only that, if possible, build a world class underground laboratory for which can look at the frontiers or open problems in the frontiers of neutrino physics. So, by and large among the neutrino physicists there was a big consensus, and all of them pitched in, and for the first few years we were exploring what type of experiment that should go in first, what is the main proposal to be put in this underground laboratory. And then once that idea became fairly clear, the theorists started looking at the phenomenology, the physics ideas, physics goals, and what are the open problems that can be addressed with the kind of detector that one was talking about. And simulations also began to provide proof of principle, and in parallel the R&D also started. And from 2003 we had some money to continue this R&D as part of feasibility study, and as you know, last several years it has taken shape and come to a stage where it can take off.
Yes. Why specifically this experiment with the iron calorimeter?
See, initially we were also looking at other ideas where for example, we also considered Waterchenko and some other type of detectors, including scintillators. Yeah. The difficulty with them is that you use a kind of active detector which is photomultipliers, very large photomultiplier tubes, which are first of all hard to obtain, and they are also very expensive. So, the goal initially was to think of a detector for doing neutrino physics, especially the atmospheric neutrino physics, in which many of our phenomenologists were also interested, and think of a detector which you can build from scratch in this country. So, the idea was then building upon the experience that we had already in Kolar gold fields, underground mines, underground laboratory, and we also had looked at a proposal earlier which was given by the Italians to be put in Gran Sasso underground laboratories called monolith. The idea was that you take these, build a stack of iron plates. Now, iron being the most dense of all and free easily available material, you could build a very heavy detector in a smaller space, smaller volume. Now, you stack these iron plates one upon the other, build it up to about 50 kilotons, and in fact the dimensions are something like 48 meters long, 16 meters wide and 12 meter high. This 12 meter would mean a 4-story high building, that is the size that we are talking about. and between these ion plates put the active detectors. There several choices were looked at, and the experimentalists decided the best choice would be what is called as a resistive plate chamber. These are cheap, they can be made from local material, and they also have very good timing, which is very critical for a detector in order to build the track length of the particles that go through the detector. So, essentially this is this rectangular thing, which is 48 by 16 by 12, which we call as the ion calorimeter or ICAL. That is the main detector in this lab.
In the area of atmospheric neutrinos, India had some pioneering work, right? Earlier. Would you mention about that?
No, see, the atmospheric neutrinos were first discovered in Kolar goldfields in 1965. It was a collaboration of TIFR, Osaka and Durham University. It was an international collaboration, as you can see. And this at a depth of about 2.3 kilometers, we had these neutrino physics neutrino detectors, which detected these muons which are produced by the neutrinos in the rock. And since there was no other muon background at that depth, it was very clear that these were produced by the neutrinos, which were in turn produced in the atmosphere through the decay of muons and the pion.
In the international scenario, we are getting a lot of encouragement from other countries and other labs. So, do you mention something about the international scene?
See, one thing is that this ICAL has a unique place in all the proposals that you have internationally. There are many proposals, and ICAL happens to be a magnetized ion calorimeter detector. This will be the largest such detector, and the nearest one is the one which is working in Sudan mines, the Minos, and that is only about 5 kilotons. It is a very small, but it is also a magnetized ion calorimeter. But the ion calorimeter that we are building is proposed to be about 50 kilotons. It will be, when it is constructed, it will be the world's massive magnet. And because it is magnetized, it has this capability of distinguishing charges of the particles which are produced in neutrino interactions. For example, a muon type neutrino will produce a mu plus or a mu minus. Now, with a magnetized ion calorimeter, you can distinguish the tracks of mu plus and mu minus because they bend in different ways. And this is unique, especially for atmospheric neutrino physics. You need such large detectors which can distinguish between these charges. And not only that, many things that many important results which have come from such great laboratories like Super Kamioka, which have seen neutrino oscillations, they are all the results have come out by putting all the results together, both for neutrino and anti-neutrino. I think there is a place fundamentally to establish that these oscillations take place both in neutrinos and anti-neutrinos. And then there are other important open questions like the mass hierarchy of the neutrinos, which is heavier than which, this is an open question. So, whether it's direct mass hierarchy or inverted mass hierarchy is something, if certain parameters are favorable, this ion calorimeter will be able to do it. But of course, as in any experiment, it depends on certain parameters which are still unknown. So, it's a frontier. It's a frontier where there may be some risks, but if you are able to get these results, it is something which is going to have a big impact on the frontiers of neutrino science.
So, many of these neutrino experiments have to be done underground to eliminate the background, and so we have to think of a site which has some overburden. So, below a mountain. So, what sort of site is India INO proposing?
As you know, for example, Kolar goldfields would have been one of the best places, it is deep underground, etc. But it is not something that is suitable because it cannot be used anymore because the mines are not operating, it is filled with water, there are so many problems, and most important problem for us is, we can't take this huge 50 kiloton material into the mines. So, as a result, we have to look for a new place where you can construct this underground laboratory called INO, as we call it now, India based Neutrino Observatory. So, what we are looking at is a place where there is a vertical rock overburden of more than 1000 meters, which is necessary to study atmospheric neutrinos and also useful for other experiments, and all round cover of at least 1000 meters of rock. Now, if you want all round cover of 1000 meters of rock, you need a vertical cover which is in excess of 1000 meters, unless it is a plateau. Okay. So, such plateaus are not easily available, or they are not even there. So, we are looking at a place where this kind of overburden is available, and also to reach the lab below that vertical overburden, we have to build a tunnel, and shorter the tunnel, the better it is. Then of course, we have to look for a place where the rock is compact, because of 1300 meters of rock overburden, the stresses will be huge. So, geologically that place should be favorable for building such a lab. And not only that, whenever you look for sites in near mountains or on top of mountains, you also have forests, you have wildlife. So, you should also look for a place where such concerns are also minimized. So, we looked at many places, and initially we had thought this place in Nilgiri mountains, northern part of the Nilgiri mountains, which are very sharply rising, very steep. There within a 2 kilometer tunnel, we could have obtained a vertical overburden of 1300 meters. And not only that, the place had extensive amount of technical data because of all the other tunnels that were there, and a campus which was already ready made. Now, we did not get permission for this, so we are looking at a new site. We are exploring the mountains in the Theni district, more precisely in the Kambam Valley. There again you have very steep mountains, and one more thing that I did not mention is the humidity factor. You see, higher the humidity, it is more difficult to operate your detectors. So, therefore, we need a place where it is a low rainfall area, steep mountains, geologically stable, with the required vertical burden for our physics. If you look around, there aren't too many places where you can get it. Fortunately, though there is not much data available in this place in Theni district, the vertical overburden and whatever you can gather geotechnically from the surface, it seems to be a good site for locating our observatory. Not as good as the one which we had earlier in mind, but this will do. But of course, it is a green field there, because there is no campus, there is no housing, though road access comes fairly close, about 2 kilometers from the site. You still have to make some amount of roads, and you still have to carry out your detailed investigations, which if a place is well known, it is not necessary. So, while there is some expenditure in terms of cost and also time, that site near Theni looks a reasonable site, and we are hoping that we will get the permission. One has to do all the statutory clearances. You have to get clearance from the forest, environment, and we are committed to doing this project in a way that it will be environmentally friendly. At least in the new place, environmental impact may not be that important, but nevertheless we have to keep it in mind, and we have to do it in such a way that it becomes, as we have always thought, that it becomes a project which becomes an example to others to follow.
All these basic science research projects are very competitive internationally. So, you need to do things also very fast and try to hope to get results very soon. Now, Professor Murthy, can you give us some idea of the length of the tunnel that will be involved in this?
Yes, the new place that we are looking at, new site that we are looking at in Theni district, the tunnel length is very similar to the earlier proposed site. It is about 2 kilometers or maybe even slightly less than 2 kilometers. And the overburden is also very similar. It is close to 1289 meters as opposed to 1299 meters in the old place. So, in terms of your satisfying your physics requirement and the access, it is very similar. But at the same time, the deep inside the rock characteristics we do not know that well. It is expected to be good, but only a full geotechnical study will tell you that, and we are planning to do that.
Proposed diameter of the tunnel?
The tunnel is about 7.5 meters wide, and at the center it will have 7.5 meters height, but it will be a dome like thing at the top. After going vertically for some distance, it will have a dome like thing, arch as they say, and it will allow two-way traffic, like 2 trucks can go, one in each way. And it will also, the tunnel is the lifeline for the laboratory. So, it is not just a vehicular tunnel. It carries your ventilation pipes, your air conditioning pipes for the laboratory. It will carry electrical ducts, it will carry water lines, sewer lines. So, in some sense, that is the lifeline. It carries everything that goes into the laboratory. And just before the portal, there will also be some servicing area where you have a utility building and a local surface facility, surface laboratory. We will also have some, we will have to build some accommodation for the people who are going to man this. Though the number is small, you need it. And then you also have guest house and hostels for students who are the most important people as far as this laboratory is concerned. It is the young people who are going to do the experiments in this place.
The tunnel basically leads to the cavern where the experiment will be done. So, what is roughly the size of the cavern?
The cavern, you see, the cavern has to be big, because you are putting a 50 kiloton huge magnet in that place. So, we are thinking of about 26 meter wide, which depending on the rock conditions, sometimes it may be only 24, 26 meter wide cavern, 132 meters long, and the height will be somewhere between 25 to 30 meters, which we will know after doing detailed engineering studies. The idea is that this 50 kiloton ICAL detector will initially occupy about half the space. So, the rest of the space in this laboratory can be used for other experiments, and there will also be a control room where you have electrical and computer controls for the laboratory, and it will also have some space where you can put smaller experiments. In fact, there are proposals for other smaller experiments, and who knows, after all we are talking about an underground laboratory. ICAL is one of the experiments. Tomorrow you may have experiments proposed by geologists and biologists. We must be prepared for accommodating more and more and interesting experiments that can be done in an underground facility like this. It is a special condition which you cannot create every now and then. Once you are creating it, you should create it for keeping long term use in mind.
Already some Indian physicists are thinking of having a double beta decay experiment, which looks at some other properties of neutrino, which are also very important and fundamental. And so, similarly, we are hoping that in future there will be other groups will propose experiments which can be housed in this observatory. So, we are all earnestly hoping that that we will very soon get the go ahead for construction, so that the tunnel and the cavern can be started. And roughly what sort of time it will take once you start, let us say today, digging?
So, let us say time 0 is when we have got all the statutory clearances and the money is assured. Then I think the first 9 months will go in what is called as the pre-construction stage, where you have to do tendering, you have to finalize all your design details, and then the construction of the tunnel begins. The tunnel will take about 2 years to construct, maybe a little more, and the cavern will take 1 more year. So, this will bring it down to about 4 years for the construction of tunnel, cavern, and in the 5th year you start outfitting the laboratory. You have to build all the facilities, and then simultaneously you can start in situ construction of your detector. So, the detector is planned to be in 3 modules. Each module is 16 by 16 by 12. So, 3 modules together make that big 50 kiloton magnet. So, in the 5th year the plan is to assemble this first module, get it working, get the proof of principle in everything, and then assemble the other 2 modules sequentially once you have confirmed everything with the first module, that everything is working and the laboratory is functioning properly. So, that will take another 2 years. So, overall you are looking at about 7 years, but the data taking can commence with the first module itself.
So, Professor Murthy, along with this atmospheric neutrino experiments, this ICAL also in future plans to do something more with the neutrino beams. Would you tell us something more about that?
Yes, you see, we have looked at physics from, we have divided the physics studies into 2 stages. The first stage is the atmospheric neutrino physics. There, apart from getting more precise limits on the neutrino parameters, we want to look at these questions of mass hierarchy, and also there are other questions on what is the octant value of one of the parameters, one of the angles. So, apart from those questions which you can study to some extent with atmospheric neutrinos, there is a very interesting proposal of establishing long baseline neutrino physics, long baseline neutrino experiments. So, the idea here is that the neutrinos are produced in the laboratories, let us say maybe in CERN or in Japan, in the accelerator laboratory in the Japan. So, intense neutrino beams are produced, and these are sent to the detectors which are very far away. And in fact, the ICAL detector in INO will be an exciting detector to study the effect of these neutrinos coming from the beam, interactions of the neutrinos coming from the beam. Another advantage that INO has is that the distance to CERN in Geneva or to JPARC in Japan is almost identical. They are not very different. They are both around 7,000 kilometers. Now, this distance 7,000 kilometers is called as the magic baseline. It has a certain advantage because it reduces at least one parameter among all the parameters that you are looking at, and therefore, it reduces the certain degeneracy of the parameters. So, you can study some parameters better because it is not influenced by other parameters. Now, there is a worldwide study which is going on for designing such a neutrino factory. These are called neutrino factories because they produce high intense beams which are well controlled, unlike we have no control on naturally produced neutrinos like in the atmosphere or in the sun. But these neutrinos are produced in laboratories, in accelerator laboratories. So, we have much better control on the neutrino beam. We know the spectrum of the neutrinos. So, therefore, if you detect the neutrinos in ICAL detector at INO situated in South India at this magic baseline, then there is a certain level of precision you bring to the measurement of these parameters. And of course, this is a worldwide experiment in which not only ICAL at INO, there may also be other detectors on the way. This is little futuristic in the sense that the idea may start fluctuating about 10 years or 15 years from now, but it is really an exciting idea. It is an exciting area in which many of our phenomenologists are working, looking at the physics goals of such a long baseline experiment. At the same time, many experimentalists worldwide, including scientists from INO, are talking or involved in the discussion of setting up such a neutrino factory in either CERN or in Japan or maybe even in the USA. If it is in US in Fermilab or some other place, we have one of the biggest advantages for this ICAL detector, which is the neutrinos produced from there pass through the core of the earth. which is a high where you have the highest density of matter, and the matter effect on neutrinos can also be studied when you have beams going through the Earth's core.
This is very true that many countries in Europe, USA and Asia,
this is a worldwide effort.
Both experimentally and theoretically are getting attracted to do neutrino physics, and lot of experiments are already on. So, what would be your advice to a student who is joining to do research in physics now about the future?
I am very optimistic, because look at it this way, this is the largest basic science project that has been proposed in this country. It is also a very large collaboration. We have some 25 institutions involved already, or which has expressed interest in being part of this collaboration. We already have nearly 90 to 100 people in the collaboration, and so therefore, this is really I mean on the scale of things that we had before, when this project comes, it will become an example for such big projects in basic science. And I am sure many more such projects will follow, and once basic science experiments start going on stream like this, it will give opportunity for our students to do hands-on experiments and participate in hands-on experiments in frontier areas. It may not be just INO, it may be something more. The people are already thinking of gravitational waves experiment. So, I think it will lead to an exciting period, especially for our students. They have places to go, they do not have to always think of going abroad to some big labs. They will have opportunity to work in big labs in the country itself, do things by their hands. I mean, like ICAL, everything has been developed from scratch, and the R&D which has progressed to a level where one can build a huge number of detectors is phenomenal, and all this has been done by young people already. So, I think it augurs well for our students, present students and future students, that such INO and such labs come and really expand basic sciences in a very big way.
That is very true, and this is also true that the INO experience has brought many institutes, universities and IITs, people doing different types of research together and to work on the same platform and bring a cohesive effort in India's goal for doing better research.